Okay, so let's take a look here. What I want to show you today. Let me get your attention, please. How about everybody? If you need to, go ahead. Like I say, just go ahead and turn your desks a little bit. I want to see attention up here. Thank you, thank you. Okay, I want to show you a couple things today. I want to show you. First of all, I want to introduce what it means to deal with not systems of linear equations like we talked about the other day, solving systems of linear equations, right? And we talked about how to do that graphically by crossing the lines on our calculator, and there's an assignment up that's going to have you do a bunch of practice with the graphic calculator. It's very simple stuff. I mean, it's kind of, but I want you to know, just get some practice continually throughout the year. Get practice and get better and better at using that graphing utility. Okay, then also we talked about analytically or algebraically how to solve these things. We reviewed how to solve them using substitution or elimination. Okay, and what these amounted to, remember, the solutions were just the intersections of the lines, right? Okay, so now we're gonna push this forward and we're gonna apply the same idea to systems of linear inequalities instead of linear equations, right? And let's open that up by just maybe reviewing real quick what the graph of a linear inequality looks like. And we just dealt with these pretty recently. In general, what's that graph going to give us? If we graph a linear inequality, there's really two parts to it. What are they? Just describe it. I won't even make it. But just kind of describe what's the graph of a linear inequality in two variables look like, x's and y's. Okay, there's a line, part of it, sure. What else? What's the other part that's new and different from a regular linear equation? What's that? Oh, say it again? The shading, yeah, right? We're going to shade a half plane. So the solution represents that boundary line, maybe. The boundary line is going to be there. It may or may not be included in the solution, but there's always going to be a boundary line and then a shaded half plane, right? Okay, so to graph these things then, we just first of all started with the boundary line. So in this case, if we have the inequality y is greater than or equal to -3/2 x plus 1, we'll just treat the equation, right? The boundary line is going to be the line y equals -3/2 x plus 1. Is this boundary line going to be shaded, or is it going to be solid or dashed? How come? You're right. How come? What do you think, Cammy?
It's the y is able to have points online, so that when
You're exactly right. What tells us that in the inequality? What part is saying, okay, this is definitely solid? What do you, when you look at this? Yeah, okay, good. The equal sign is included with the inequality. Good. So the line is a part of the solution. So step one, we're going to graph the boundary. That's easy enough. This is in slope-intercept form, right? Y-intercept is, everybody agree, is 1. Slope is what? -3/2. We always go left to right, so we got maybe a point starting at the y-intercept right there, and we're just going to drop down 3 over 2. Get a second point, connect and extend. There's the boundary line. All that's left to do is just shade the correct half plane. Now there's two ways we can look at this. First of all, how about the shortcuts? Can anybody tell us all what the shortcut is? If I have an inequality in slope-intercept form, how do I know very quickly which half to shade?
Put your 1 and 1.
Go ahead, John.
Or put 1 and 1 or 0. Just take a point and then.
Okay, so we can do the test point. Let's do that first. We can take a test point. What's the easiest one to check always? 0, 0. Okay, so if we test the point 0, 0, if I plug that in, 0, 0, what do I get?
0 is bigger than or equal to 1.
Okay, is that true or false?
False.
False.
It's going to be on the other
It's
side.
false, so we're going to shade away. Very good. So we'd shade then this side over there. Good. Okay, what's the other? So we can test a point always. That's always a safe bet. But there's another really quick way if we have a linear inequality that's written in slope-intercept form. Now, if it's written in standard form, this isn't going to work. But if it's written in y equals mx plus b form, and it's not equals this time, it's an inequality instead, but if it's in that mx plus b form, what's a really quick way to just know immediately if I'm shading above the line or below the line? Remember anybody? Okay, it's this. It's the direction of that inequality sign, right? If y is greater than mx plus b, think what that's saying. We're going to shade all the y values that are greater than, that means above, doesn't it? Because y is the vertical axis. So that means all the values above mx plus b, the line. If it's a less than, we're taking the values below, because it's a vertical issue, right? And so in this case, we know right away, because y is greater than the boundary line, we're going to shade above. So we pick any point on the line and draw an upward arrow, and that's pointing to the region that gets shaded. Does that make sense? Okay. So there's our quick review. That's how we graph the solution set of a linear inequality, right? No big deal. And you guys have had lots of practice, and you've done very well with that. Whoops, that's all I want to do. Do that. Okay, line solid. Tested a point, didn't work, so we shaded away. Very good. Okay. Okay, we can skip that stuff. So what about graphing a system? All a system means is more than one inequality, right? So what if we're going to graph two? What do you suppose we do? Graph them both, right? So we've got these two lines here. If we take the first one, first inequality, this is not written in slope-intercept form. So do you remember the trick? If we've got this thing in standard form like this, right? So here's the first one. I'll write it a little bigger. X minus 2y is less than or equal to 3. And let's just take the boundary line for a moment. I won't even write the inequality. Let's just take the boundary line. Okay, that's written in standard form. Remember, that's ax plus by equals c. We're going to see a lot of that, this unit. Okay? A, b, and c should be integers. If it's written in standard form like that, what's a really quick and easy trick for graphing the line? We can always put it in y-intercept form, and that's fine. People like to do that, and that's okay to do. It's fine. But there's a really quick and easy trick that I showed you guys, which oftentimes works really well. And you can always go to y equals mx plus b form. Do you remember? We just need 2 points is all we need, right? We can connect and extend. If it's written in this form, it's really easy to find two special points, the intercepts. How do I find the x-intercept? What's unique about the x-intercept of any function? Okay, meaning, okay, take out the y. What's always true of the y-coordinate of an x-intercept? If it's an x-intercept and it's intersecting the x-axis, what's the value of y every place on that axis? 0, right? So if we let y equal 0, then we can just cover up that term, right, in standard form and solve for x. Well, x is 3, right? So that's easy. So we got 1 point, 3, 0. And then the y-intercept would be where x is 0, exactly. So we can just cover up the x term in standard form and solve for y, and we get what? Okay, -3/2, so we're down -1.5, so right about there. And so this is my boundary line, and it's going to be solid, isn't it, on this first one? So it's just going to look like that. Does that make sense? Okay, and then we have to decide which side to shade. Now this one is not in slope-intercept form, so we got to pick a test point. Which test point are we going to pick? 0, 0. Okay, is 0, 0 going to pass? If I pick 0, 0, I get what result? 0, 0 gives me what on the left side? 0, right side I get 3. Is 0 less than or equal to 3? It is, so we're going to shade that side. So that's our first inequality, right? Okay, so let me erase my messy chicken scratchings here. So that's what we get for the first one. Now the second one's pretty easy to do. Solid or dashed line? Solid. It's in slope-intercept form, so where's the y-intercept? -4, slope of 3, so we can easily get 2 points to graph that one, right? Y-intercept in a slope triangle. Which one gets shaded this time? We don't even need a test point. We shade above or below? Above, okay. They used a test point, but that's fine. Okay, now what do you suppose is the solution of the system then? Because remember what a system means. It's an and statement. If we go back to our equations, we want the values of x and y that satisfy the first equation and the second equation in our system. So what do you think? Yes, sir. Oh, okay, go ahead. What do you mean? Okay, that's part of it. There's more to it though. Yes, sir.
Anything above both lines.
Okay, good. So it's going to be the double shaded region, right? All the places that are shaded both red and blue would be the parts that would satisfy both inequalities. Does that make sense? And so let's think about that. So that's going to be this sort of big pie-shaped region up here, right? And what about that line right there, that boundary line? Is that going to work? That's going to work, isn't it? Because the blue boundary line is in both the blue and the red region. And up here, this red boundary line is also going to work, isn't it? Because that's inside the blue shaded region. Now, is this boundary line down here going to work, this red piece? That's not going to work, is it? Because that's not blue shaded. And this blue part of the boundary line up here won't work because it's not in the red shaded area. Right? And so if we want to just only graph the double shaded regions then, it just looks like that, doesn't it? Including the boundary lines, because they're solid. Make sense? Okay? So we can have lots of inequalities in the system. It's fine. Now how many, just make a prediction for me here. If I've got 3 inequalities, how many overlaps are we going to need for this solution? 3. So we're going to need the triple overlapping region, if it exists. If there isn't a triple overlapping region, then there's no solution, right? Okay, 2 of these are really easy to graph. Describe the boundary line here. X is less than or equal to 0. On the x-axis? Okay, I think you're on the right track. Yes, sir. It'll be vertical, and it's going to be the y-axis, isn't it? It's going to be the line x equals 0. So that's going to be a line with an x-intercept of 0, so it's vertical, right? And what about the line y equals 0? Now what's that, Cammy? Second one. X-axis, good. That's the line y equals 0, so it's got a y-intercept of 0, so it's horizontal, right? Those are really easy to graph because the boundary lines are so simple. Which part is going to get shaded in this first one? We've got the boundary line that's the y-axis. Pretty obviously here, am I going to shade to the left or the right if I want the values of x less than or equal to 0? The left, right? So negative, all the negative values of x. And then pretty obviously here on the second one, if I want the values of y greater than 0, am I shading above or below the x-axis? Above, okay, good. So we got right away, we get that for the first one, right? We get that for the second one, so we got this overlapping region, but there's a third one to do, right? Now let's use our trick. Let's use our cover-up trick here. That's in standard form. Where are the intercepts of this third boundary line going to be? Where's the x-intercept going to be? Where's it going to be if I cover that up? Right, there's the equation, the boundary line. Remember, if I let y equal 0, that term goes away, and the x-intercept is -2, and the y-intercept is? -2. 2, okay, solid line, right? So there's the x-intercept, there's the y-intercept. So there, the green line is the boundary line. What do I do to shade on this one? It's like a broken record. It keeps going over and over. We know what to do here. What do we do to pick which side to shade? Test 0, 0. If I plug 0, 0 in, I get 0 is greater than or equal to -2. True or false? It is? That's true, isn't it? Because greater than means to the right of on a number line, right? So we're going to include 0, 0. So we shade that side. So what's the triple overlapping region?
Very small.
Yeah, just that little tiny triangle in there is it. Right? That's it. And all the boundary lines in this case were solid, so they all get included. But they might have been, some of them, could end up being dashed also. Okay? All right, so that's how we do this manually. Now I want to show you how to do this using a graphing calculator as well, because there's a really slick way to do this. On the assignment, I'm going to ask you to do a little bit of both, because I want you to know how to do it manually, but I also want you to know how to do it with a graphing calculator. So if we go back, I'm just going to maybe even pull up. I'll just pick a couple of these problems that we did on the slideshow. Whoops, and we'll look at these with a graphing calculator. Okay, so how about, we can skip that one. Let's do a system. Okay, so what about this guy? So if I want to graph this system of these two equations, all I have to do, now the problem is with this, if I go up to y equals, these are built for equations, aren't they? These aren't built for inequalities. Okay, but there is an app that you all probably have. If you don't, I'll be sure to give it to you when we go down to the lab. If you go to apps and you scoot all the way down to the i's, and there's a shortcut for doing that. If you hit alpha and then I is right here, you see that?
Yeah.
If I hit alpha I, it'll skip down to the i's, and it's either called inequal or inequal z. Okay, so that's the one that we want. If we hit enter, it's going to say, okay, great, press any key to continue. And look what it does. It changes things a little bit. It does two really important things. Before I get into this, though, I'll also caution you that inequal z removes some capabilities from the calculator as well. I don't think, for example, the fraction template works in inequal z. Okay, and there's some other things that it does that are a little bit funky. So really, you only want to use inequal z for graphing linear inequalities. When you're done with doing that, I would get out of it. Okay, yes, sir. Oh, not question. Okay. So first of all, notice that in the upper left, it gives you an x equals button. Now watch what happens. If I go up to that and I hit enter, look, it gives me x1, x2, x3, etc. So you can actually graph vertical lines or inequalities with vertical boundary lines, which you can't normally do on the graphing calculators. That's kind of nice. If I just hit y equals, I can get right back into the y stuff. The other thing it does is whenever the cursor is over the equal sign, it automatically brings up these function buttons down here. And to access those, you always, what do you suppose you push to access those? Which button?
Second.
Not second. Seems like it might be, but it's the same as with the other pop-up buttons. It's alpha. Okay, alpha is the button you use to access those. So for example, on this first one up here, let's do, actually, I tell you what, I'm going to turn this around just a bit, and let's do, how about instead, I'm going to do this one first, okay, because it's so easy, it's already in slope-intercept form. So if I want to put that one in, I need the greater than or equal to sign, right? So I'm just going to go alpha, and then I'm going to push, in this case, F5. So that's the one that corresponds to the greater than or equal to. And then I just put it in normally. Now I'll scoot over, and I'll just put in 3x minus 4. And if I hit graph, if I go zoom 6, look what it does. Isn't that cool? Graphs the inequality. Okay, and it even puts in a solid boundary line. If that had been just a plain old greater than, that would have been a dashed boundary line. So it does this, it is really slick. Okay, but we're not done. We want to add the other piece to the system. Okay, so now on this one, we gotta be a little careful with this one because it's not in slope-intercept form. It starts off in standard form, right? So we're gonna do what we practiced the other day. We're gonna solve this into the calculator, right? We're gonna have a numerator on the other side. We'll collect everything into the numerator and then divide by the coefficient. Remember that little trick we were working on? So on Y2, now because you can't use the fraction template, let me make sure that's the case. I really don't think you can. If I go alpha F1, it doesn't pop up, does it? Okay, so I won't, let's get rid of that then. Oops. Can I not get? Oh, well, okay, I guess it's off now. So I'm gonna open up a set of parentheses for the numerator. What's already on the other side if we're looking at the top equation here? 3, okay? Notice I haven't put in an inequality sign yet either. Why do you think that's the case? Say it again? Okay, because it might flip, right? If I divide by a negative, it's gonna flip anyway, so we'll save that till the end. When you're doing inequalities, it's really a good habit to get in, is just do the inequality last, because it may end up flipping. So we got 3 on that side. What am I gonna do to get the y by itself? I'm gonna, first of all, subtract x. Good, I gotta subtract the first term, the x term to the other side. Now what? What button do I push? I heard it. Say it again. Parentheses, gotta close the parentheses. Divided by what? -2. Okay, gotta use the negative sign. And then what does that do to the inequality sign? It flips it. So I'm gonna go back to the equals. Too far. There we go. Go back to the equals, and instead of a less than or equal to, it becomes a greater than or equal to. So I'm gonna go alpha F5. Agreed? Yeah. And now if I go zoom 6, and I could change the window if I needed to, but we'll just try zoom 6. There's the first inequality, there's the second inequality, so you can see the overlapping region. Now would you agree that's kind of messy though? Yeah. It's kind of messy. Okay, check this out. You can make this, you can clean this thing up. If you go to the shades button up here, so we're gonna go alpha, and then that's a really wide button. Either F1 or F2 counts as the shade button. Take your pick. Then I've got 3 options for shading. I can do the original shade, I can graph the union, which is everything that's shaded for either one. Or what I want is the inequality intersection, right? I want the part that's double overlapping, that's overlapping with all of them, right? So I'm just gonna type a 1, and look what it does. It'll regraph, there's the first one. Now it'll erase away everything that's not included in the second one. Isn't that cool? Isn't that cool? So now we can see look at that, we can see the solution. That's a really handy way to do that. And you can still navigate around on this screen and get lots of good information. For example, it might be useful, there's an application that's called linear programming that I really don't think will do. It's just something that kind of, you guys are all gonna take calculus anyway. And so this calculus is a way better technique. But watch this. If I want to know where the vertices are, okay, attention please. Okay, oh, you guys are showing or something. That's fine. But don't miss this because this is kind of cool. If I want to navigate through and find where the vertices are, because there may be multiple vertices. If I have like 3 or 4 boundary lines, there could be lots of vertices to this region that's the solution, right? Lots of corners. All I have to do is hit trace. And it's going to take me through all of the important points. Like there's one right there. There's an intercept. If I go hit the right arrow, oops, hang on. I think maybe it's the up arrow. Oh, I thought that worked. Hang on. Down. These always kind of confuse me, but I thought there's a way. Oh, I know what it is. Never mind. It's intersection. That's it. If I go second, calc, intersect, first curve, second curve, and if I make a guess, I can go right up here. I don't even need a guess because they're lines. See, it'll tell me it'll tell me the coordinates of that intersection, so I can still find the vertices pretty easily. Does that make sense? And I think there's even another way, so that's one way I can always do it. Oh yeah, there's another way too. Watch this. If I go, okay, so if I go graph, and right down here, point of intersection trace. This is the one I was looking for. This other big white button that takes F3 and F4. If I go alpha, F3, or F4, it's going to find me the points of intersection. So if I just toggle around on the screen, it's giving me, there's only one point of intersection here, so it'll find it pretty easily. But by hitting, notice this is the intersection of Y1 and Y2, and I've never, if you guys figure this out, tell me, because I always just kind of push until I get the one that I want. I'm imagining that maybe the horizontal arrows control the first function and the vertical ones control the second one, as I'm guessing what's going on. But once you figure it out, you tell me. But just by hitting kind of the up arrows, yeah, see that switched, and the right and left arrows, it'll jump around to the different vertices. And I've just never figured out what the pattern is. I haven't really looked that hard, but there probably is a way you can do it more efficiently than I do. You guys tell me, you'll figure it out and tell me what it is, I'm sure. Yes, sir.
Do you have a PowerPoint that tells us how to do this on the graphic calculator?
I don't, but I now have, because I've been taping this, I now have a YouTube video that explains it. Okay?
Okay.
So that'll be up on the site. I'll put it up today. Okay? Alrighty, so I think we're good to go. Let's head down to 205 and you guys can practice this stuff.